we have to discuss C procedures for two samples or two populations. Still, I mean, up to chapter 8, we discussed just one sample or just we consider one population. And for that particular population, we were interesting about mean, mu, variance, sigma squared, or standard deviation, sigma, something like that. Or for the hypothesis test, we used mu. Okay, and last chapter we use population proportion. Okay, so we discussed these things only for one sample or one population. In this case here, in this section, we are talking about different population, more than one, just in case it is just two populations. Okay, so we are considering two populations. They are totally different. I mean, they have no relation. We this let's say population X has nothing to do with population Y. Okay, so something like that. But in this case, we are not going to consider individual parameters like mu, sigma square, something like that. We are considering the differences between those two. Okay, we are not going to consider what happened in the mean mean in population 1 or mean in population 2. We just consider difference between those parameters. Okay, C procedure mean for most of the time we can use C score, that idea, but sometimes we have to go beyond that. Okay, let's talk about that. Two sample problems. So in this case, we need to compare the parameters for two distinct populations. They are different. Okay, these populations are different, like this. This is capital X, this is capital Y. These are two different populations. Okay, there are parameters like here it's gonna be mu X, sigma X. Here it's gonna be like mu Y, sigma Y, something like that. Okay, their parameters are, which mean their mean, their standard deviation, they are different, but we need to compare their parameters. Okay, observations are independent. As I mentioned, population right here has nothing to do with population right here. Okay, you will be having a clear picture in next few slides. Unlike the one sample cases, which mean what we have discussed so far, we are not interested in individual parameters. Okay, we are interested in seeing the parameters for the populations are equal or different. Okay, which mean mu X equals mu Y, something like this. Okay, not exactly this one, but something like this. Or their difference equals to 0, or their difference equals to some value, some constant, something like that. Okay, these are the basic assumptions. Consider one population. This population we call capital, let's say capital X. It has these observations or these samples from X1 to Xm. There are m number of samples. Okay, so they have a random sample from a distribution. A random sample mean they are independent. Okay, with mean mu and standard deviation sigma, mean mu 1 and standard deviation sigma 1. Okay, another population, from another population we have random samples y1 up to yn, so they have n number of samples. Okay, its mean mu 2 and standard deviation sigma 2. Okay, so the sample x and y are independent, independent to each other. Okay, so here random sample based on these observations. Okay, these are this random sample mean they are independent for each other. Okay, in third line in this bulletin they have mentioned these two right here, this one and this one, they are independent. Okay, clear? Okay, So here we have population 1, size equals to a capital N, and we have another population, let's say population 2, size is capital M. So let's say this one is capital X, this one is capital Y. Okay, so we are taking observations, M number of observations. Yes, it's going to be M. This is going to be N. Okay, so we are taking M number of M number of simple M number of observations from population 1 right here as our sample. We call it sample 1. Again, we are taking another sample from population 2, N number of observations, N, simple N number of observations. So it is our sample number 2. So you can see there is no relation between these first sample and second sample. Okay, they are different. They are independent samples. Okay, these are independent samples. Okay. What happened? Okay, so now I'm going to discuss what is the distribution of x1 bar and x2 bar. Okay, so this x1 bar means mean of this sample, x bar. Let's say x1 bar is the mean of this sample, and x2 bar is mean of this sample. Okay, don't confuse with this x1, x2, or x and y. Okay, x1 bar and x2 bar, or we can replace this by y. Y bar. Okay, okay, so if I don't know, yeah, it's there, x1, which means this sample is normal distributed. Okay, yeah, they have mentioned sorry, they have mentioned x1 has a normal distribution with mean mu1 and variance sigma 1 squared. Okay, same here, x2 is normal distributed, mean mu2 and variance sigma 2 squared. Okay, you know that okay, x1 and x2 are independent samples. Or if you are confused with this x1, don't mix this x1 and x2 with these. Okay, with these x1s, they are different. Okay, or you can, it's like x bar minus y bar. Okay, that's the case. Okay, if you compare with previous slides. Okay, these two are normal distributed. So if you remember, what happened to the x1 bar? It is again normally distributed, right? Mean is mu1. What happened to this guy here? It becomes like this. Okay, so doesn't matter. It doesn't matter. Okay, x bar again, if x is normal distributed, then x bar is again normal distributed. Okay, normal distributed. Okay, so difference between these two guys right here, x1 bar is normal distributed, x2 bar is normal distributed. So I can say that x1 bar minus x2 bar, they have a normal distribution. I'll show you the parameters later. Okay, like summation, mean, just sum, something like that. So this guy right here, it also has a normal distribution if x1 bar has a normal distribution and x2 bar has a normal distribution. Okay, otherwise story goes different. Okay, okay, let me erase this. See, if it is like that, the parameters x1 bar minus x2 bar has a normal distribution with mean mu x bar x1 bar minus mu x2 bar, comma, variance is, or standard deviation right here, x1 bar minus x2 bar. Okay, let's say this one, variance. Okay, so mean, you can find the difference between those two, but keep this in your mind, don't swap the terms. If it is x1 in front, then mean also belongs to x1. Okay, don't change them. Okay, if you need to find x1 minus, x1 bar minus x2 bar, then mean x1, mean from x1 bar comes first, minus mean x2 bar comes second. Okay, it doesn't matter for this one because it is just summation. So if you need to find the standard deviation, it's going to be like summation of their individual standard deviations. See, sigma 1 squared over n1 plus sigma 2 squared over n2 square root. Okay, this one, sigma 1 squared over n1 square root is what? Standard deviation for x1, right? STD for not x1, x1 bar. Remember, I showed you a few seconds ago. This is belongs to second sample. Okay, so it's like summation of those two. Okay, so this guy right here, from the notations we used, we can say, okay, x1 bar minus x2 bar has a normal distribution with mean this one, variance this one. Variance is square root of this one. Variance of x minus y. Do you remember this one? This gonna be where? Do you remember where if x and y are independent? Okay, if x and y are independent, we can write this like this. Do you remember that?
Yes, sir.
That's the reason we have something like this. Okay, if x and y are independent, we can write variance of x minus y is equals to variance of x plus variance of y. Okay, actually this came from, if you remember, I can write it here, x minus y, variance of x minus y equals, if you don't know whether they are independent or not, we can write it variance of x plus variance of y minus 2 times their covariance. But if x and y are independent, this piece goes to 0. There is no covariance. That's why we have that variance of x plus variance of y. That's the reason we have standard deviation like sum. Okay. Okay. Okay, let me erase this again. This difference x1 bar minus x2 bar is normally distributed. Okay, mean this, you can see mean is this one, mu1 minus mu2, and standard deviation is this one. Okay, here it is not just x1 minus x2, it is mean x1 bar minus x2 bar. Okay, or simply x bar minus y bar. Okay, sample, two sample means. This again we can show using central limit theorem, CLT, central limit theorem. If we have a large enough sample, it doesn't matter, we don't need to think about x1 is normal distributed, x2 is normal distributed. If they are large enough samples, like first sample is 100, second sample is 200, then no problem with that, we can assume those two are normal distributed. Okay, regardless of their distributions. Okay, standardized. Okay, now do you remember this word standardizing? Remember that in last, I think chapter 4, Yes, we did something like this. We standardize our variables if they are normal distributed. X minus mu divided by sigma. Do you remember this one? This is the mechanism or machine that we use to standardize. Okay, each normally distributed value we can convert to a standard normal using this mechanism. Okay, so same here we are going to use C. Capital C is the we denote by standardized, we denote by capital C. What we need, this one. This is just considered as a one term. Okay, x1 bar minus x2 bar is a just one term. So you can plug it into here like this. See, here it is just one term. Minus, now you don't have just one mean, you have two means. So they are means. It's like x1 bar minus, x1 bar minus x2 bar minus mean x1 bar minus x2 bar. Okay, they are means. Divide by their standard deviation. Their standard deviation is sigma x1 bar minus x2 bar. Okay, same thing. It's similar to this one. Only the parameters are different. Okay, so so that this capital C has a what? It has a standard normal distribution 0 1. Normal 0 1. So again, since it has a standard normal, you can use your C tables. Okay, you can see now we which side we are moving. Okay, so since you have standard normal distribution, then you can use your C tables to deal with this kind of problems. Okay, let's check this example here. Suppose that you have we have 40 faculty members were selected from private institution. Okay, 40 from private institution. Again, 45 from public institution. Okay, let's say this one is simple N, this one is simple M. They are different. Okay, they are different samples. Both populations are normal distributed. Okay, they have given both are normal distributed. Average salary for the faculty members. So average salary for the for this one, let's say private institution, I'll consider mu1. Then the other one, public institution, I'll consider mu2. Okay, so not mu2. Let's say x1, x2. This is x1. This is x2. Okay, so private institutions, I'll consider capital X1. Public institution, I'll consider capital X2. So based on their salaries, faculty members or private institutions, which means belongs to X1, it is 98. So this is mu1. Okay, then public universities, it is 93 mu2. Okay, I think standard deviations, those values are from thousands. Okay, private institution standard deviation is $2, which means sigma 1. This belongs to public university, it is sigma 2. Clear? So we have all the necessary values. What we need to find the distribution for the difference. See, for the difference of the sample mean salary. Difference of sample means. Sample means difference of sample means mean mu1 minus mu2. Okay, clear? Difference of the sample mean salaries. Clear? So if you need to find this, this is not the mu1 and mu2. This is going to be x1 bar minus x2 bar, right? Because we are talking about samples. Okay, So this is going to be not mu1, mu2, this x1 bar, x2 bar. Okay, just don't confuse with the parameters. Okay, since we are dealing with sample, we are considering x1 bar and x2 bar. We need to find this, what not just the value distribution. Okay, since they are normally distributed, okay, x1 and x2 are normally distributed, you know that in theory, you know that this difference should it has a normal distribution with mean mu x1 bar minus x2 bar, comma, standard deviation x1 bar minus x2 bar. Okay, so you know this is true, but you need to figure it out what are these values. That's you have to calculate using what you using the last two equations. So x1 goes to the private institution, x2 goes to the public institution. Okay, so these values are given. So mean difference is the mu x1 bar minus x2 bar. Standard deviation you can find using this, right? So here sigma x1 is sigma x1 squared is 2 to the power 2, sigma x2 squared is 3.5 to the power 2. These are the sample size. So once you calculate this, you will get this value. Now you can write, okay, x1 bar minus x2 bar has a normal distribution. Why normal distribution? Because x1 and x2 has a normal distribution. Okay, mean 5, standard deviation 0.61, or you can write it like variance, mean and variance. Okay, so it has a normal distribution with mean 5 and standard deviation 0.61. Okay, clear? This is I think this is not in your notes. I'll upload this one. Okay, I just edit these notes. Clear? This is how we find the distribution of x1 minus x1 bar minus x2 bar. Okay. In summary, we were talking about population and sample. We know that we just consider samples from different populations. Okay, two populations, two samples. Okay, x1, x2 from capital X1 and capital X2. Okay, their mean, mean of x1 bar minus x2 bar is this one. Remember that we are interested about this x1 bar minus x2 bar. Sample mean difference, not just x1 and x2. Okay, so their standard deviation you can find like this. Standardization, C, capital C, using this. This is the mean difference. This is the sigma. Okay. Then C has a standard normal distribution. Clear? Okay. So that's about how to find the distribution. Previous few slides I have summarized here using proposition. If easily we can get this proposition using a central limit theorem in chapter 5. Expected value of x bar minus y bar, we can write it like this. Since they are independent, you can give the expected value for each of them, and it's like this, right? Expected value of x bar is mu1. Expected value of y bar is mu2. Okay, mu1 and mu2 means population mean. Okay, so expected value of sample mean equals to the population mean. Okay, same case here for the variance. This is for the variance. As I mentioned, since they are independent, you can write it like this. And once you simplify it, once you plug the values, you can get this. And standard deviation, just the square root of variance. Okay. Okay. Now we are moving to the C test for the two samples. Normal populations, with this case we have no known variance. We know what are the variances of them, variance or standard deviation, whatever. Okay, we know these two. Additional assumptions. Okay, this is not an assumption. This is something you should do. C, how to calculate C, I mean how to standardize, you should know this. Okay, has a standard normal distribution. Yes, this has a standard normal distribution with mean 0 and 1. This is the standardization process. Okay, clear? Because sigma, we know these two values. That's why we are talking about known variance. Populations are normally distributed. Okay, populations are normally distributed, then samples are normally distributed. That's the case. Okay, these are the general hypothesis tests. Again, we have 3 tests, but only difference is this we are considering difference. Okay, we are considering difference. This is the population mean, and this is the population. This again, sorry, this is the first population mean. This is the second population mean. Okay, so they are like this: mean 1, sigma 1. Here, mu 2, sigma 2. Okay, this is the population. Population, let's say 1. This is population, let's say 2. Okay, they are 2 different populations. Okay, so we are interested about their mean difference. Population mean difference. Okay, population mean difference. So in the hypothesis test, always you remember that for the null hypothesis, everything, whatever it is there, is equals to something. Okay, so same here, this difference equals to something. This is a value. Okay, this can be 0 or any other value. Okay, it can be negative value as well. It's a real value. Okay, in this case, I mean in this 2 sample case, null hypothesis is not necessary to equal 0. Okay, it's always equals, but not necessary to equal 0. Can be any value. Okay, alternative hypothesis, if we have one tail test, let's say this one upper tail, right? So, okay, if we have upper tail, it's going to be mu1 minus mu2 greater than something. Okay, if lower tail, alternative hypothesis is mu1 minus mu2 less than something. Okay, in 2 tail case, definitely not equal. Okay, this is the general case. So we can convert this to a usual case, something what we have to use most of the time. Okay, you should remember this one. Okay, but in some cases, okay, if some cases you will see that in questions they have mentioned, you need to figure it out whether there is a mean difference or not, or mean difference is greater than 0. I mean, there is no mean difference, something like that. So at that point, we can simplify that delta 0 is equals to 0. So that, remember the last slide, mu1 minus mu2 equals to delta 0, right? For the null hypothesis. Once, if this equals to 0, you can rewrite this mu1 minus mu2 equals to 0, which means mu1 equals mu2, something like that. Okay, so we can replace all previous 3 cases like this. Okay, so sometime you need this, most of the time you need previous one. Okay, general case. Clear? So this is same as the uh, cases what we have learned so far. So I think in this chapter we don't have to do all the cases. I have mentioned in slides. We have done this in chapter 8, so we don't need to do that. We just skip that. Okay, I mean skip me not doing it in the class. So it is easy. So case 1 is populations are normal distributed and variance are known. Variances are known. So that your C statistic is something like this. If you have two populations, X and Y. Okay, clear? So at that time, your H naught is what? Here, what is this X bar and Y bar? They are sample means. Okay, so sometimes you need to deal with sample means. Sometimes you need to deal with population means. Okay, clear? It based on your problem. Most of the time we have to deal with sample cases because in real world we are using samples instead of populations. Okay, so x1 bar mean sample mean from x population, y bar mean sample mean from the y population. Okay, so hypothesis test. Okay, this is not the place. So this is the place. Hypothesis test. Null hypothesis is what? X bar minus y bar. Again, here it is general case, so you don't know which you have, like H naught always equals. So I'll write X naught only. This value right here. Okay. So if you before you solve this C statistic, you have to assume H naught is true. Clear? So most of the time you will be having this value right here. Replace it, and you have this value as well. Okay, we will do not this one. We will do example for case number 2. Yes, so that you will get a clear idea. Okay, don't confuse with the parameters. Clear? So if these are mu1 and mu2, so don't confuse with that. Appropriate rejection region, you can use using p-value approach or critical value approach, using how we did in the chapter 8 and chapter 8. Yes, chapter 8. Okay, clear? Okay, case 2. We don't know the population, but we have large enough sample, which mean m greater than 0 and n greater than 0. Believe me, if you cannot use if you have m greater than 40 but n less than 40. At that point, you cannot use this this approximation. Both samples should greater than 40. Okay, remember that. Like here, right here. See, m and n greater than 40. At that point, you can use the same thing, but at that point, you don't know the variance. See, variances are unknown, so you have to use the S instead of sigma. Okay, and you can approximate to a normal distribution, then do your work. Okay, same as case 1. Again, we have done it in chapter 8. I think, yeah, we have example here. Check this example so that you can cover both cases, case 1 and case 2 using this example. There are 2 samples. Eat fast food, no and yes, right? You can see between these 2, yes and no's, there is no relationship. If it is yes, yes. If it is no, no, right? If it is yes and no, there is no answer like that. So they are different. So sample sizes are given. Let's say this one n, this one equals to simple m. Sample means, see, sample means this is x bar, this is going to be, let's say, y bar. Okay. Standard deviations are given. This belongs to sigma x bar, this belongs to sigma y bar. Okay, so my samples are x and y. Does this data provide strong evidence for concluding, okay, this is our conclusion that we need to figure it out. Average, true average calories intake for teens who typically is fast food exceeds that of those teens who don't by more than 300 calories per day. 300 exceeds 300. What exceeds what? True average. Yeah, true average is this one, 300 for teens who typically is fast food exceeds that that of those teens who don't buy more than 300 calories per day. So exceeds mean it's less than. Okay, this one. This definitely one tail test. Okay, which side? That's the case. Exceeds. So researchers claim is exceeds. So greater than. So alpha is given. See, alpha is this one. Okay. Exceeds. Greater than. Okay. Okay. Check this one. First, I mean, focus on first 1, 2, no, 1, 2, 3 and line 3 and 4. Not 3 and 4. 3, 4, and 5. Okay. Okay. First, I'll explain these two. Mu1 and mu2. Mu1 belongs to typically eat fast food. Mu2 goes to say no. Do you remember? Yes and no. Okay. Do not typically use fast foods. Okay. So check this one. These 3 points are really important. H note. Okay. For this H note, we use, in general, we use true means. I mean, yeah, true means. True means mean population mean. Okay, that's why we denote mu. So you have to consider, I think in example, yes, true average calorie intakes for these 2 typical fast foods. Yes, see, true average calories. True average calorie means here sample calories. See, you can see according to this one, it is sample, right? But we need to test mu, true average calorie, which means mu1 and mu2. Okay, that exceeds this value or not. That's what we have mentioned here, here and here. Okay, true value. But to do that, we don't have true values, right? We have sample means. So we replace sample values to this equation and solve. That's why here you can see x bar and y bar. Okay, we have to figure it out these two by using this. Okay, we assume that H naught is true as always. Okay, clear? As always, we assume H naught is true. If just think about, if we replace x bar and y bar using mu1 and mu2, okay, there is nothing to do with that. There is no calculation because numerator goes to 0, right? So nothing to do with that. That's why we replace using, this is just one term, using sample means. Okay, so you know n1, you know n2, sample means given, so easily you can plug values here. This delta note is 300. Delta note is 300. So plug these values. Okay, Again, please don't mix, don't swap these terms, x bar and y bar, okay? If you consider mu1 minus mu2, then x bar minus y bar. Again, you can change this term. It doesn't matter if you consider for the h naught, if you write mu2 minus mu1, totally fine, okay? Because here they have mentioned difference greater than this. So difference can be mu1 minus mu2 or mu2 minus mu1. That's fine, okay? If you change this term right here, you have to change this term as well, okay? Then you get this value. You have what is this? What is this one? I don't know. This is not alpha. I think alpha is 0.025, right? This one. Based on alpha, I think they, yeah, critical value. They have used critical value. You have C value here, C test statistic, and find the corresponding C value based on this, which means C alpha. So it is 1.96. 1. Okay. 1.96. So comparing these two, you can take your decision whether we reject or not, do not reject. This value right here, 1.96, is greater than this one. This is what kind of test? This is greater than, which means this. So your C alpha is somewhere here. Your test statistic value is somewhere here. Your C is somewhere here. So what you have to do? Do not reject, right? Which means we do not reject H naught at this significance level, O alpha 0.025. Therefore, we do not have enough evidence to say that claim, researchers claim. Okay? Clear? Everything is very similar in chapter 8 and chapter 9. Instead, these first few steps. Okay?